Hello and welcome back to my YouTube channel. This is Cheyenne, and today I'm going to solve a deflection problem using the momentary theorems in structural analysis. So this question asks us to determine the deflection at various points and rotation at various points for this beam using the moment area theorems. And you have to note that the stiffness is different for the middle part of the beam and also the cantilever parts of the beam, as we see. So let's go ahead with a step-by-step procedure to see how we can solve this problem. In our first step, we're going to find the reactions. So we have done this before. So what we do, we just kind of put our beam together like this, and then we remove the kind of supports there, kind of like the free body diagram there, just some arbitrary directions right there. And then after that, we take the summation of the moments about any of the points. Practically, we can do any points, but of course, to make our life easier, we do about points C or E. Doesn't matter, any of them you can go with. And then, as you can see, I have considered the counterclockwise direction as my positive sign convention. I start from the left, I say 20 multiplied by 3 because I'm taking my moment about point C. It's in the counterclockwise direction, so positive 20 times 3. Then you go on, and then Cy does not create any moment about point C because it goes through the point, lever arm is 0. And then you move on. Okay, another load here. This is a concentrated moment, so it's 100 kilonewton meters, and is in the clockwise direction, so you just put negative 100. And remember, it's not 100 times 3, okay? This is just a moment, it's not a force. And then you move on, no force. Okay, here I have another force, Ey. So Ey, say, okay, multiplied by this distance here, 7.5. Right, and so Ey times 7.5, it will be in the counterclockwise direction because it's turning this way. And then you have this 40 kilonewton force right there. This 40 kilonewton force multiplied by 3 plus 4.5 plus 3, which will be 10.5. And this is creating a moment in the clockwise direction, as you can imagine. And from here, you're going to isolate for Ey. And you'll find out that Ey is 61.3 kilonewtons. After this step, we can actually take the moment about another point, or we can just write the summation of the forces in the y direction. And I will do the summation of the force in the y direction because it's much easier. So I'm just going to, again, start from the left side, considering that the upward direction is my positive sign convention. Negative 20 plus Cy. This is not a force, right? This is a moment. Plus Ey, and Ey, I just found it before, right? So 61.3 minus 40. From here, again, you isolate for Cy, and you find out what this number is. This number, this is a negative number. What does that signify? It means that initially, we arbitrarily just assumed a sign convention for Cy, which is arbitrarily said just this is going up. Negative here just indicates that this is not going up, but it's going down, right? So it's 1.3 going down. So what can I do? I can just erase this, and I'm just going to kind of draw an arrow like this going down, and that is 1.3. So this is how we find their reactions at this step. For our second step, we're going to draw the shear force and bending moment diagrams. For a more detailed video on bending moment diagrams, I have provided a link in the description section, and you can check that video out. Practically, we don't really need the shear force diagram here. We only want to work with bending moment diagrams. So if you can actually go straight from the, the beam situation, like the beam that you see here, to the bending moment diagram, I would say absolutely go for it. But again, these types of questions, especially for momentary theorems, the question is pretty straightforward, because usually momentary theorems are more useful when you have a series of concentrated loads or concentrated moments or something like that. So you won't really have much of a problem drawing the shear force diagram anyways, right? It won't take that much time. So at the end of the day, it won't make that much of a difference. But again, at the end of the day, we need the bending moment diagram. We don't really need the shear force diagram. And if you actually want to draw the bending moment diagram from scratch, I've actually done a video about that as well, and I'll provide the link in the description section as well. So let's go ahead and draw the shear force diagram first, and then we'll do the bending moment diagram. So first, we have our axes, and then you start from the left side. So from A to B. Any load? No. So just go 0. There you go. Then at point B, we go straight down 20 kilonewtons. There you go. That's 20 kilonewtons there. And then from B to C, no loads. Okay, continue. At C, we have to go down by 1.3. So here, continue. We go down by 1.3. right? Now we have negative 21.3. And again, from C to D, nothing. So we just continue again. But also from D to E, there's nothing, right? Remember that this 100 kilonewton meter doesn't really have much of an impact on the shear force diagram, right? So it will have its impact on the moment diagram, but not on the shear force diagram. So from C to E, there's no change in shear, okay? So the value just remains the same. At point E, we go up by 61.3. We end up with 40 kilonewtons. E to F, there's nothing. And then after that point, you know, we go 40 down to 0. And since we start from 0 and we finish at 0, that kind of indicates that we did our shear force diagram correctly. And from here, we just move on to our moment diagram, okay? And also before that, we also put like our kind of lengths here, because as you know, we draw our bending moment diagram directly from shear force diagram with this method, right? If we are doing like the moment diagram from the shear force diagram. So we'll need these lengths. And now we do the moment diagram. So at first, you have no area here. So again, remember that the area under the shear force diagram is the change in moment. So anything here or any concentrated moments here, no, nothing. So the area under this is 0, so the moment is 0, right? And at point B here, I see that there's a change in, well, there's shear, like there's the area under the shear force diagram. That means that there's a change in the moment, bending moment diagram, basically. So what is this area? This is 3 times negative 20. That's negative 60. So you go down by 60 here. And as you remember, if this is a constant line like this, then it will be upgraded like one level, like one order, basically. So 0 order to first order, and first order is like basically a line. So next we have this kind of this part. And you might be tempted and say, I can just say 7.5 times this value, which is negative 21.3. But we have to keep in mind that in the middle there, we have this concentrated moment. So it is in our best interest to kind of separate this part and say, okay, this is 3 times 21.3, right? So I'm just going to say negative 60 minus 3 times 21.3. I'm going to get a number there. So there's a line there. But at this point, I have to move up by 100 kilometers. Why am I moving up? Because it's a clockwise direction that I have here. And we know that based on our conventions for the moment diagrams that we are drawing, clockwise represents a jump in the bending moment diagram. So you're going to jump by 100. I'm going to go to negative 24 kilonewton meters. After this point, you calculate the area under this, 4.5 times 21.3. So negative 24 minus 4.5 times 21.3. You get this value. And after this, you have this area, 40 times 3, which is 120. You add that, you get to 0. And that means that we did our moment diagram correctly as well. For step 3, we're going to draw the M over EI diagram. So this is the step that is kind of new, because previously we did we did find reactions before, we did find bending moment diagrams before in the previous courses for strength of materials, but for this one, this is kind of new. But it's not really complicated. So this is our moment diagram, right? And the only thing we're going to do, we're going to say, okay, we know what our EIs are. We don't know the exact values, and we don't need to, but we do know that from A to C it's EI, from E to F it is EI, but from C to E it is 2EI. So basically what I'm going to do, I'm just going to say, okay, these are kind of constant. So the section that's going to really change is this section, this kind of highlighted section that you see here, right? So what I'm going to do, I'm going to kind of keep them the same. I'm going to, again, divide them by EI, but the values, like it's going to be negative 60 over EI, negative 120 over EI for this section and for this section, right? So I'm just going to separate that. So you see, so I'm just going to separate that. And then for this part, whatever value I see, I'm just going to divide them by 2EI. So I'm just going to say negative 60 over 2EI, negative 124 over 2EI, and so forth. And so you see, negative 30 over 2EI, well, negative 60 over 2EI, which is negative 30 over EI, and so forth. You just find all these values one by one, right? So it just all corresponds to each other, see? And this will be our M over EI diagram. So simple as that. Again, any part that has the EI, you just keep it the same. Remember that C, for example, is shared between ABC and CD. So from the left side, it's going to remain negative 60 over EI. But from the right side, since it is 2EI, this one will be divided by 2 as well. So negative 60 over 2EI, which is negative 30 over EI. So just keep that in mind for the shared points. So this is how we do our m over ei diagram. In step 4, we're going to draw the elastic curve based on the moment diagram. I'm going to talk more about the momentary theorems and their nature and like how they work and so forth. But for now, we just have to know that the momentary theorems are based on a graphical method. So that means that we need to know the elastic curve or just how it looks really to help us understand the question, right? So the theorems themselves actually help us a lot, and they indicate a lot in terms of how like the elastic curve is drawn itself as well. So we can, those are our checkpoints, but it's always very helpful initially just to know how to draw the elastic curve from the beginning and make our life much easier. And this is probably the most crucial step in our process for solving this question. So how can we draw the elastic curve? Well, in this case, the moment diagram that we have here, and by the way, I didn't really pick the moment diagram for m over ei diagram that we have here because we don't really need that. I mean, you could do that if you want. It doesn't really matter. At the end of the day, the direction is not going to change, and all that matters for drawing the deformed shapes from the moment diagram is the sign, not the values. So what we're going to do, we're going to take a look at our bending moment diagram, and from there we're going to draw the deformed shapes. How do we do that? Well, based on our sign convention, negative moment means that it is concave down, right? Something like this. Positive moment is concave up. Now in this case, we're actually, kind of in a good position because we actually don't have to change the curvature here. It's all pretty much the same. So like it's all negative at the end of the day, right? So it doesn't matter if it's like increased, if it's like negative 24, 60, it doesn't matter. At the end of the day, it's all concave down. So effectively, what that just means is that from F to A, or actually let's not say A, because A you would say, okay, wait a minute, this is 0. So let's just keep this for now. But from this point till this point, you have concave down. So you just have to kind of draw an elastic curve like this from here to here. Maybe this is not drawn the best way, but again, this is going to be curved more a little bit here, maybe, right? That's more natural. And here again, it's going to be curved more. We can keep that in mind. Again, for the purpose of this question, it's good enough. But yeah, so this is how it's going to look. Now for AB, you're going to say, wait a minute. We said positive is concave up, negative it is concave down, which is what we did. But what about AB? AB is 0. Well, remember from the superposition video, we mentioned, I'll put the link in the description as well. But from the superposition video, we said, okay, this part does not have any load, so it's nothing. So when it doesn't have any load, it means that there's no curving here, so there's nothing there. Moment is 0. It's just going to continue to be the same way. So see, it's just going to continue. The slope will continue. The rotation will continue to be the same way. So whenever you are at the end of a cantilever or overhang situation, and beyond like one point, you don't have any load, you just continue that the same way it is. And you can easily just experiment this with a ruler or something. You can just apply a load, and then you will see that part is not curving really, like the end part basically there. So this is how we draw the elastic curve based on a moment diagram, and it is very, very crucial in solving our problem. Now that we have all these basic information, we can actually go ahead and kind of solve our problem, and we can find an initial point to determine the required rotations and deflections. What do I mean by initial point? Well, let's actually go ahead and talk about the momentary theorems themselves, right? So I'm just going to recap the momentary theorems here. So there are two theorems here, Theorem 1 and Theorem 2. Theorem 1 is basically just states that the change in slope between 2 points is the area under the m over ei diagram. So remember the m over ei diagram that we had? So basically, this theorem just states that the change in slope between 2 points is the area under that diagram between those 2 points. So if you want to find the change in slope from A to B, you just find the area under the m over ei diagram between those 2 points, and that's it. And in this case, by the way, theta b with respect to A, theta a with respect to B doesn't really matter. So both of those are the same value. So b with respect to A with respect to B doesn't really matter. And this is how it looks. It's just integration. So this just effectively means that the area under the m over ei diagram. That's basically it. And one very important thing is the sign convention. So when we say theta b with respect to A, or A with respect to B for that matter, if it's positive, that means that it is counterclockwise, the change is counterclockwise. And if it is negative, the change is clockwise. Remember that for our scenario, the M over EI diagram is always negative. So basically the change from left to right will be always clockwise. Basically, this is what's going to happen. And so as you can imagine, if we go from left to right, our life is much easier. Why? Because we say, so actually I'm just going to show it here, right? So to simplify things, if you write stuff like this, you can kind of think about cancellation, numerator, denominator, not in reality and actuality, but just for the sake of understanding. This is A here, for example. So I always, and by the way, see, I always go from left to right. So to simplify things, always go from left to right, okay? So I'm going to say, okay, A is on the left, B is on the right. I'm going to say okay, theta A plus theta B with respect to A and A cancel out. You end up with theta B, okay? It just makes sense, really. And you might say, wait a minute, so I could have just put like theta A with respect to B here. Yes, you could, right? There's no problem. But I just put it this way so that it is, you know, more understandable. So I can just show this cancellation here like that, right? So, but the important thing here is that you go from left to right. Can you go from right to left? Absolutely. But in that case, you have to kind of go with negatives. So you have to say theta B minus theta B with respect to A gives you theta A. Do you really want to do that? Well, maybe it obviously works, but we always want to keep stuff simple. So I would always say go from left to right, and you always have to just add. So just say theta A with respect to the area under the diagram is equal to theta B. And in this case, you don't have to worry about signs or anything. It's just always plus, and we're good to go with that. So that was our first theorem, which is related to the change in the slope, and we basically use it to find rotations, really. That's it. The second theorem here talks about the vertical deviation of one point with respect to a tangent drawn from the other. So this can be a little bit complicated. So what I'm going to do actually, I'm going to kind of put these ones. I'm going to talk about these positive and negatives as well. But for now, I'm just going to, so when we talk about TA with respect to B, this means deviation of point A to the tangent drawn from point B. Okay? So TA with respect to B is like this. So you're going to draw a tangent from point B. When you get to point A, just draw the deviation. Okay? And remember, previously I mentioned theta B with respect to A and theta A with respect to B are the same. But that is not the case for TA with respect to B. So TA with respect to B and TB with respect to A, they don't have to be equal, and in a majority of cases, they're not going to be equal. Okay? So again, TA, this understanding is very important. Deviation of point A, so TA with respect to B means deviation of point A with respect to the tangent drawn from point B. Okay? And so that's how we get this value. And how do we find that value? So, okay, so that is T of, the deviation of point A with respect to B. How do we find it? Well, you go to your M over EI diagram again, but in that case, you're not going to just take the area. You're going to say it is the moment of that area. So you're going to say that area multiplied by the distance from point A. Okay, so I'm going to show it in an example which makes more sense. But so let's say for this one, you have like an area under the M over EI diagram. You're trying to find A with respect to B. You're going to take the area under the diagram here, so whatever it is, right? You're going to say area times the distance from the centroid of this area, because it's the moment, right? The lever arm, basically. The lever arm, basically, which is like from here to point A. Okay? So previously, so for the first theorem, it was just the area. For the second theorem, you also multiplied by a lever arm from the centroid of that area that you have to point A. Remember that it is with respect to point A. Okay? So it's just the first kind of expression that you see here. And also, let's talk about the sign convention. This can be a little bit confusing, so if you feel like this part especially is a little bit confusing, just leave that. If you don't really need it, it's a very good confirmation, but as we go through the problems, it will make more sense. But I'll just mention that when like you see that T of A, kind of the deviation of point A with respect to B is positive, that just means that this point A that we are evaluating is just above this tangent drawn. Okay? And remember, I talked about conformations for the elastic curve that we have drawn, or for the tangents that we have drawn. This is where it comes kind of handy, right? Because if we have drawn our elastic curve, we don't really have to worry about like the negative and positive, because we can see it. But maybe let's say we made a mistake in the drawing the elastic curve, and you kind of get a different value here. Maybe you get like a here you see something like this in your diagram, right? But wait, I got a negative value. Well, that means wait a minute, maybe we made a mistake in drawing our elastic curve. So that's where the sign convention comes in handy, right? That's very important there. But if you draw your elastic curve correctly from the beginning, this won't really be much of an issue. So, and of course, negative here, negative tangent means like this, right? So again, tangent A with respect to B. Well, deviation of A with respect to B. So here, you draw this. It just means that this point, A, is below the tangent. So A above the tangent, A below the tangent. That's all negative and positive mean here. Also, when we want to use the formulas for the momentary theorems, we have to keep in mind the limitations that we have. So for example, the moment area theorems that we have are driven from the elastic beam theory, and elastic beam theory of course has its own limitations. The beams must have linear elastic behavior, we should have homogeneous materials, plane sections remain plane. Also, for momentary theorems deviation themselves, we need to state that, well, actually for the second theorem specifically, we need to assume that the deformations are small so that we can make some approximations. So that's also another limitation. And also we are neglecting shear deformation since the length to depth ratio is sufficiently large. This is also related to the elastic beam theory. So just some limitations on the usage of the momentary theorems. Now that we know our theorems and we have our basic information, we can start and find our rotations and deflections. Initially, always I start with rotations because it's easier to find, and then we'll move on to deflections. So first, we'll need to find any of these rotations, but the thing is here, so you might say, okay, let's go just use the first theorem. But the thing is, to use the first theorem, you have to have one rotation at least, right? So here, so I basically have it here. So once the slope for any one point is found, the first theorem can be applied to determine the rotation for any other point. So we can't really use the theorems directly to find like just a rotation and deflection at any point. They give us information, and we just have to work with that information to find what we need. So you might say, okay, how do we come up with that initial point? What do I choose? Well, for beams that include a simply supported part and initial slope is not known, but we can actually use the second theorem, surprise there, between the two supports to find that, right? You might say, wait a minute, the second theorem is for deviation, and that probably is related to deflection, isn't it? Well, we can actually use the second theorem because it's just a deviation, it's just a length, right? So we can actually use that to our advantage to find our rotation as well if we need to. How can I do that? I might say, so see here, I talked about here, simply supported part. Between those 2 points, just kind of find TC with respect to E or E with respect to C. That's it. So anytime you have a simply supported scenario and you're looking for rotation at any point, first thing you're going to do is go to the simply supported part and just find TC with respect to E or E with respect to C, okay? And for us in this case, we actually need theta C anyways, right? So what I'm going to do, I'm going to draw TE with respect to C. So I'm going to draw the tangent from C and stop at E. This is TE with respect to C. Why? Because again, the deviation is drawn from E, the tangent is drawn from C. Okay? And so you might say, okay, so I got TE with respect to C. What can I do? Well, in this case, you can see the triangle here. Okay? For this triangle, I can say the tangent of this angle, which by the way happens to be theta c, is equal to this value that I have here over the entire length here from C to E, right? And based on this, I can just easily find my theta c, okay? And also, by the way, so I mentioned tangent, but since, as we talked about the limitations, we are assuming that the deformations and rotations are very small, and in the vicinity of 0, of course, the tangent and x functions are just equal. So as a result, instead of just saying tangent theta, you can just say theta. So you can just say theta c is equal to this value divided by this value. Okay. So now let's see how I can find the theta c value. Well, we talked about this. So Te with respect to c over CE. Well, the length CE will be my value. Length CE is kind of known. It's just 3 plus 4.5. So that's 7.5. That's known. How can I do this? Well, I have to go back to the theorems that we talked about, right? So it is, in this case, it will be the area. So this is the second theorem. It's T. So what are we going to do? We're going to say, first, let's write the theorem, actually. So it's going to be something like this, right? Something like this, right? So what does this mean? It doesn't really mean much to us. We're just going to have to work with the diagram itself anyways. But I'm going to say, you know what? Which is the area of concern for me here? It's from C to E, right? So from this point till this point is what I really need to consider. So this will be the area. But this area is not really like one area. It's just different areas. It's kind of composed of different triangles and rectangles and so forth. So I have to kind of separate them in some way and deal with them separately. How can I do that? Well, I'm going to say this is a rectangle, triangle, and then rectangle, triangle. Now, for sure, you could use a trapezoidal situation as well, because we know the centroid for a trapezoid as well, and there's a formula for it as well. But it's always, much simpler to just, use simpler cases, right? So to use rectangle, triangle, because for these, we actually know exactly where the centroids are without the need for a formula or anything like that. And at the end of the day, all we need to do is just find the centroid. So you can go with whatever method you choose. So again, what is the theorem here? The theorem says that first, you're going to take the moment first about point E, because it is TE with respect to C, so it's always the first letter about which you take the moment, right? So you're going to take the moment about this point E, and we're going to have that. And so we're going to say it's the moment of areas. So area times distance from E, area times distance from E. What are those distances? So if we're taking the moment about point E, the distances are like this, right? So x1, so the center of a rectangle here, from the center of this to point E, x2, from a third of this triangle, so a third from this edge here to point E again. For this triangle again, x4, from a third of this triangle to the edge, and for this small rectangle here, from the middle of the rectangle to the edge. Okay, and so one by one, we just have to find what all these values are. So we start with like the area 1 that we have here. For the rectangular area, I have what? Negative 30 over EI multiplied by length, that is 3. So that is my area there. What is the distance or lever arm? What is x1 bar? It is the distance from half of this to here. So half of this, which is 3 over 2, 1.5, plus the whole length here, 4.5. Simple as that. So 3 over 2 plus 4.5. That's it. What about the second one? Well, in this case will be this triangle, the area of this triangle. What is the area of this triangle? It's not 62 over I times 3 over 2. Okay, so it's just, you have to subtract this 30 from here. So this length is 32. So 32 over EI, or rather negative 32 over EI, multiplied by the length 3 divided by 2, that's the area of the triangle, multiplied by the lever arm, which is x2 bar, which is measured from a third of this distance. So this, in this case, is 1 meters, right? 1 meters here, because it's 3 over 3, basically. 1 plus 4.5 meters, okay? And that is what we have here. So 3 over 3 plus 4.5, that's the lever arm, and this is the area we talked about. Next, you move on to 3 and 4, and you kind of do the same thing again. The area in this case is just negative 12 over EI times 4.5. You multiply it just by this distance divided by 2, which is 4.5 divided by 2. That's what you end up with here. And for the triangle, same thing. So in this case, you have 60 over EI, but remember that you have 12 here, so just say 60 minus 12, right? That's 48. So negative 48 over EI multiplied by the length, which is 4.5 divided by 2, and you multiply it by the distance here that you have, so which is from a third here, which is 4.5 over 3 basically, right? And this will be your value, again, the lever arm multiplied by the area. And you add all these values together, and at the end of the day you get this result here, okay? But remember that this is just the deviation. What was our formula for finding theta c? It is TE with respect to c over the length. So the only thing we have to do is just divide this value by the length that we have, which is 7.5 meters. So I'm just going to do that. And from here, I get 145 over EI radians. Remember that again, negative and positive that you get here doesn't really mean much again. You know, in our, well, let me rephrase that because they do mean, but it's just that when we have our elastic curve and we know that we have drawn it correctly and we're checking it with TE with respect to C and so forth, we actually see it from the diagram that it is counterclockwise or clockwise. So from here, as you can see, this is a counterclockwise slope. So anything that goes like this counterclockwise, anything that goes like this is clockwise. Or you can see it from here. This is the initial state of this beam. It goes like that. So that means that it is kind of turning in the counterclockwise direction. Okay, but so I mentioned about a confirmation or a check from TE with respect to C. How can you do that, right? In many cases, again, you can draw the elastic curve pretty easily, but let's check that as well. So here, E with respect to C, the value is what? Negative. What does that mean? It means that the tangent drawn from, so point E is basically below the tangent drawn. Yes, makes sense. Because as we know, if this point is below the tangent that is drawn, that means that TE with respect to C is negative. And indeed, it is negative. So that's also a confirmation that you can kind of think about. And yeah, that's how you find your theta c. And remember always to put your sign here as well. It's counterclockwise, is it clockwise, and so forth. Now at this stage, we can actually go ahead and find our rotations at any point very easily, based on the first theorem, right? The only thing we need is the area under the M over EI diagram, right? So if you want to find A, B, D, E, F, or any other point, you just have to use the first theorem there. So just a recap, for finding rotations, initially you just need one point, so you just need to know the rotation for any point, right? Once you know that one point, then finding the rotation for other points is just going to be very straightforward, because you just have to use the first theorem and find the area under the M over EI diagram. So how can I find out what theta A is? Well, in this case, theta A, you might say that, wait, so this theta A, theta B, first of all, these two are the same, okay? So because it's linear. You don't have to consider that, by the way, so you can just go ahead with theta A. You're going to see why, because the M over EI diagram here is just 0, so it doesn't really matter. But so just to make my life easier, I can actually go just with theta B, because theta B and theta A are the same. As you know, this is a line. So rotations are the same between B and A. So I can just say, effectively, I'm trying to find out what theta B is. How can I do that? Well, as we talked about, you always go from left to right. So if I want to write a relationship between B and C, I can say theta B plus theta C with respect to B is going to give me theta C. Okay? Again, always go from left to right. Theta B plus theta C with respect to B gives you theta C. Okay? So just going to have to write that one, right? So this is the rotation I'm looking for here, right? There you go. And I know that theta A is equal to theta B. And this is the relationship that I can write between B and C, right? And so the only thing, so I do know what my theta C is. I can actually figure out what my theta C with respect to B is based on the first theorem. And from there, I can actually go ahead and figure out what my theta B value is. So theta C, we actually know that. So this will be kind of our equation if you can kind of move things around here. And theta C, we actually figured it out in the previous step. So I know that this much and it is counterclockwise. So the only thing left for me to do is to find theta C with respect to B. How can I do that? Well, just use the first theorem. This is it's just the area under the M over EI diagram between points B and C, right? So I go here between points B and C. What is the area? It's 60 over EI, well, negative 60 over EI, multiplied by the length, which is 3 meters, divided by 2, because it's a triangle. And, well, yeah, but that's the area. And you just kind of figure that out, negative 90 over EI. And since it is negative, that means what? That means it is a clockwise change. Remember the sign convention? If the area under the M over EI diagram for the first theorem is positive, that means that the change in the rotation is counterclockwise. If it is negative, the change in rotation is clockwise, right? So in this case, it's negative. That means that the change in rotation is clockwise. So you might say, okay, wait a minute, this is confusing. This is negative, clockwise. You just said this is counterclockwise. How can I know what to put here? Well, for this one, theta C, you know it's 145 over EI, right? This is counterclockwise. Theta C with respect to B here, this value is actually clockwise. So that means that the signs between this and this, they just have to be opposite each other. So, and you can actually kind of think about the fact that counterclockwise is positive, clockwise is negative. So you just have to say 145 minus negative 90 over EI. So that's pretty much really it, right? So just have to imagine counterclockwise, positive, clockwise, negative. That's pretty much what you need to know. Okay. And from here, you figure this one out and you will see that it's a positive value, which means automatically it is counterclockwise. And you can actually see it from here as well. So here you have this rotation here. You can see it is counterclockwise, right? It has the same sign convention as C anyways, right? Now, one thing here is that you might say, wait a minute, why did you say theta A is equal to theta B in the beginning? Did we really need to do that? And you are right. We don't actually need to do that. You can actually go ahead here. And because as you see, is there any area here? No. So because from A to B, there's no change in rotation. So that's why there's no change in rotation. There's no area under the M over EI diagram either. So from the beginning, you could have just ignored this part. Okay. And you could have just said, it is, so you could just say theta A plus theta C with respect to A is theta C. And the result would be exactly the same because the thing is that there's no area right here, right? So there's no area. The area here is 0. So you could totally do that as well. And lastly, for rotations, we're going to figure out what theta F is. It's going to be the same steps. So theta F is here. Where's the rotation? It is right here, right there. So what we can do, we know our rotation at point C. What we can do, we can just go ahead, just take out the area under the diagram between C and F, right? And then just write a relationship there. So I can just say theta C plus theta F with respect to C is going to give me theta F. Simple as that. Can you see how simple it gets when you start from left and finish it right? That's pretty much it. So kind of the same stuff. Theta C plus theta F with respect to C is theta F. So we do know what theta C value is. It is counterclockwise. What is theta F with respect to C? We just have to go to our M over EI diagram and just calculate what the area is under this diagram, which is like, kind of consists of like a couple of areas here, 1, 2, 3, 4. You can just group them any way you really want. In this case, since it's rotation, you can even go ahead and just isolate the trapezoids if you wish. So since the formula for a trapezoid is pretty straightforward as well. But actually I do that intentionally. I do this one intentionally because I'm actually going to use like all of these areas again in the deflection formulas. So especially like in an exam scenario, if you have like these values already, then that's maybe helpful in saving time, right? So you can just kind of keep that in mind as well. But so the first theorem again states that the change in rotation between any 2 points is the area between those 2 points under the m over ei diagram. And for that, you just have to kind of add all these areas together, area 1, area 2, area 3, and so forth. And so we start with area 1. It's just, yeah, simple area, so 30 times 3. And then this area of a triangle here, we've done this before as well. Area of this rectangle, area of this triangle. Keep in mind to subtract the 60 and 12 from each other. And then at the end, you have this 120 multiplied by 3 divided by 2. That's pretty much it. And add all these values together. At the end, you get this negative 480 over EI. And since it is negative, it means that the change from C to F has been clockwise. And so the only thing we have to do, which we know theta C, we know theta F with respect to C. From here, we can get theta F. So we can simply say 145 minus 480 right there. It is negative 335 over EI radians. And since it is negative, it just indicates clockwise. That's pretty much it. So in this case, as you see for momentary theorems, to find out what rotations are, always go with the sign convention, counterclockwise positive, clockwise negative. Simple as that. And we're done with rotations here. And now we can move on to finding deflections. For deflections, we can start with any point that we really want. So I'll just start with delta D here. Where's delta D? Well, delta D is the deflection here. So it's from here to here. So if I show it here. So that is here delta D that we see. But I can't really, so as we know, the only theorem that we can use for finding deflections is going to be theorem 2. So we can't really use theorem 1. Theorem 1 is only really used for rotations, because it's just changing rotation. So that's not going to be really useful for finding deflections. So we can say, how can I find out what this delta D value is? Well, I can say, you know what? I actually can figure out what this value is, right? So this value is actually, if you think more about it, it's just TD with respect to C, because the tangent is drawn from C, right? And if I just draw a deviation, it's just from here to here, right? Because the curve is here. The deviation is from here to here, not to here, because this is the initial part. And even for TE with respect to C that we had before, it's from this point, right, the tangent, to the curve. Okay, so the curve, of course, since the support does not really settle or anything, it might, but we don't have this in our case anyways. The deviation here in this case is going to be equal to this value. So from here to the curve. And same thing happens here, from this point to the curve, right? So I can actually figure that one out from the first theorem. And also, this is a triangle here. And wait a minute, I actually know what this theta C value is. Since I know this theta C value, and I know this length, I can actually figure out what this value is. So actually, let me show you all these values. This is psi, right? A value that I can find from this triangle, which is effectively, by the way, since theta C is equal to psi over this 3 meters, psi is just basically theta C times 3 meters, right? By the way, you can name it anything you want, just a name there, that's all. And this value is TD with respect to C, okay? Good news. So we can find this value, both these values, and from there figure out what delta D is. Why? Because delta D basically is just psi minus TD with respect to C, okay? So this is what we have from the shape right there. And what is psi? Just talked about that. Theta C, we know what theta C is. 3 meters is the length between C and D, right? And remember again, theta C, tangent theta C, doesn't matter. Rotations are very small, they're equivalent. And so from there, we now know one of these values. We know psi. What is TD with respect to C? Well, you just go to between the areas between the 2 points and take the area under the M over EI diagram here. We have 2 areas here. So first of all, this is the theorem right there, right? And how can I apply the theorem? Well, I have 2 sets of areas here. And I'm going to take my moment about which point? About point D, right? Always about the first letter. So I'm going to take the moment about point D right there. Okay, so that's the point right there. And I'm just going to have to also figure out what is x1 bar and x2 bar. So x1 bar is there, x2 bar is there. We have actually kind of worked with these, well, not with x1 bar and x2 bars. We have worked with area 1 and area 2. But so we've calculated area 1 before. So it's like just 30 times 3. That's the area of a rectangle. Multiplied by the distance, which in this case is x1 bar, and it's 3 over 2 basically, right? So 3 over 2, which is the lever arm from point D, from the centroid of the rectangle to point D, multiplied by the area for the rectangle. Plus, the same thing applies for the triangle. It's going to be, again, this 32 times 3, right? So 3 times 32 divided by 2, that's the area of the triangle, negative, of course, multiplied by x2 bar. And x2 bar is the distance, so a third from the edge, 3 over 3. So this value is 3 over 3. So it's going to be 3 over 3 multiplied by this value, right? The area under the, well, the area for the triangle, basically. And from here, if you add them up together, you're going to get this much deviation, okay? So I know the deviation, t d with respect to c. I know my psi, so I can just say psi minus this. It's going to give me delta d. One very important thing here is that for finding deflections, we can actually see how they look like. So you see, although you get this like positive value, which doesn't really mean anything, you get this negative value, which again just means something else. It just means that the point that I have here is below the tangent. Okay, good. That's all this negative sign means. So when you're gonna put these values into the equation, just keep that in mind. Go with the diagram. Okay, don't go with the negative and positive sign because they don't really help us really. So, and in fact, if you put them with signs, you're gonna end up with the incorrect answer, right? So in other words, always go with absolute values. Don't go with negatives at all. Why? Because in your shape, you have this, right? You know this, you see this, right? So you have your psi, and you know from the absolute value of psi, if you take out this absolute value for t d with respect to c, you can actually figure out what your delta d is. So again, forget about this negative value here or here for that matter. So just the absolute value there. You just kind of subtract them from each other and you get this value. And this deflection is, as we can see from the shape, it is upward. The initial state of the beam, and this is the deflected state of the beam. Okay, and that will be your deflection. Now we can figure out the deflection for another point. So let's go in this case with delta F, right? How can I do that? Well, as you can see, I don't have anything here right now, right? But there are a couple of ways to do that, of course. For example, you can imagine if I do have theta E, for example, I can just go ahead and say, okay, you know what? I'm just going to draw a tangent from E. It's going to look something like this, right? Something like this. And then from there, I can write a relationship there, right? So because this distance will be TF with respect to E. This distance will be like a value from the triangle, which again you can call psi. And the deflection would be this value plus this value. But the thing is, you know what? We don't have theta E. So why go through all this trouble and find theta E and then go ahead and just apply all these? We can say, you know what? We actually know what theta C is. So what I can do, I can draw this tangent, right, from C. I just continue this till point F, right? So first of all, delta F is of course this, but if I continue this tangent here, right, T F with respect to C is the value from here to here, okay? And this value will be psi, okay? And the psi value, I can actually figure it out from this triangle that you see, Okay. So as you see, the procedure for finding deflection based on moment area theorem is very similar across these multiple cases that we are doing. It's just always figuring out where the deflection is exactly, figuring out where the psi is, and figuring out where the deviation is that we are taking. Okay. And also you can take any two points that you wish, but you always want just make your life easier. Of course, you could go with E. You could even go with A if you have it. It's fine. But first, you always want to be as close as possible to that point, because in that case you don't have to do as many calculations, but not for any cost, because in this case we don't know theta E. In that case you have to use the first theorem again, find theta E, and that's just too much hassle. So we just kind of went with the most kind of efficient way to solve this problem. So that was delta F. This is TF with respect to C. Then you have this kind of psi value there. And so as you can imagine, this delta F is just TF with respect to C minus this psi value. The psi value is pretty straightforward. So it's just theta C multiplied by the length, right? Because we are dealing with this triangle there. So psi is just theta C multiplied by this length there. This length is, in this case, 10.5. So this is the relationship, of course, we have for finding delta F. Psi is this much. We know what our theta C value is. And from here, we can actually figure out what our psi value is. Now, the only thing really remaining is for us to just find TF with respect to C. How can we find that? We know based on the second theorem, we go to our M over EI diagram between points F and C. So this is C, this is F. We're going to take the moments about the first letter, point F, right? And how many areas? Actually, we have a lot of areas. We have this area, this is all. Let's group these areas again. So 1, 2, 3, 4, 5. Again, a combination of triangles and rectangles. And by the way, you see here, that's why the moment area theorem is mostly used for a series of concentrated loads. Because as you can imagine, if you have like distributed loads, you have what? You will have a parabola in your moment diagram, M over EI diagram as well. And although you can, of course, find the, kind of centroid for that one, but it's just too much work, right? You have to go to the formula sheet. Okay, where's the area for a parabola? The centroid for a parabola, the area for a parabola. Okay, write the formula, multiply it together. Is that case? Is it that case? It's just too much work, and you might as well be like, you know what? Why am I using the moment area theorem? There are more efficient methods than moment area theorem for kind of solving distributed loads, for example. So this is also the reason that it's more efficient to use the moment area theorem for series of concentrated loads. So in this case, we have these areas. The only thing we have to do, again, x1 bar, a1, x2 bar, a2, so forth, something like that. And also, I think I've forgotten that there's also that x5 bar times a5, so just keep that in mind as well. And so one by one, you just put all these values together. So say, again, you take the moment about point F, the first letter. And so, and also, yeah, I see there's a typo here as well. This is TF with respect to C, by the way. But yeah. So in this case, we just go ahead and take this area. So this area again is 30 times 3. It's 30 over EI, by the way. So I'm just mentioning. So it's negative 30 over EI times 3 multiplied by distance and so forth. Where are the distances, by the way? x1, x2, x3, x4, x5. It's just, again, the distance from the centroid of that specific area to the point about which we are taking the moment, which in this case just happens to be point F. So for us, for example, area 1, it is just the distance from here, 3 over 2, plus 4.5 plus 3. Simple as that. Okay, so just do the same thing for all these other points here. So for triangle here, we have kind of done the same thing before, so I'm just going to skip these two as well. But for the third one, it might be new, so I'm just going to do this one. The area for this is basically 3 times 120 over EI negative divided by 2. That is the area. Multiplied by a distance. The distance, remember, it's from a third from the edge. So a third from the edge, this is the centroid, right? So this is 1 meter. This is 2 meters. So the distance is actually 2 meters from point F. Okay, so just keep that in mind. So the area, which is here, multiplied by the distance. And distance, as you see, is 2/3 from the sharp edge here, or 1/3 from this kind of flat edge that you see. Okay, so 1/3 from here or 2/3 from here. Again, at the end of the day, we're measuring the distance from the centroid to point F. And you add all these values together, and you get this value. And the only thing we need to do right now is just kind of put them back into our original formula that we had. TF with respect to C, the value, psi, the value. Remember again, negative and positive, we don't care. We always work with absolute values for the last stage of finding what our deflection value is. So again, forget the negative. 2347.5 minus the value we got here, you get the deflection for point F. Again, I want to also emphasize that again, if, let's say for this question, you were actually requested to find what theta E was at first rather than theta C. In this case, absolutely. Just draw a tangent from theta E, okay? And in that case, you would say that this delta F is actually equal to psi plus TF with respect to E, okay? In that case, that will be much easier, okay? But in this case, we did not know what our theta E was. As a result, we just went with the value we already knew from before. Also remember to include the sign convention here. So it's going down, right? So how do we know that? Well, we just look at the shape here. So original state, deflected state. So it's going down, as you see. Simple as that. Just put a downward sign there, and that's it. And lastly, we can figure out what the deflection value is for point A. So we're going to kind of use the same idea that we did before. So in this case, again, you have this. So the delta A, where is it? Delta A is here, right? Now, what are we trying to do? We're trying to kind of use the second theorem again to figure out what this value is. In this case, I can say, you know what? For theta C, I know my theta C value. So what I can do here, I can just say, I can draw a tangent from this point, right? Like that, right? Again, this curve is not drawn the best way. So maybe you can, in reality, it has more curvature here. But again, for the prior purposes, it's good enough. But, when you're drawing it on your own, you can just curve it a little bit more here. So that makes more sense. But at the end of the day, the idea is that there is a distance here, of course. And that distance is what? It is TA with respect to C. So deviation at A with respect to tangent drawn from C, right? Which is this blue line that you see here. So that will be TA with respect to C. And this value will be like psi, right? Again, just a parameter there, which we can find based on like the geometry here is like theta C multiplied by this length that we have there. So that is that length. And you have another length right here. So we can say that delta A is equal to psi plus TA with respect to C. In this case, that's what we have. So psi, we can easily figure it out. Theta C multiplied by the length. Length is in this case 4. Good to go. Now, what is this TA with respect to C? It's just going to be the area under this M over EI diagram multiplied by the centroid for each of those areas. How many areas do we have here? We only have one area, right? So it's an integration. This is the only area I have. And I do have an area here as well, but it's 0, right? So there's nothing there to kind of take into account. So in this case, I can say that I'm going to take the moment first about point A. That's the first thing to do, right? And why are we taking about point A? Because again, this is the first letter that we are discussing. So take the moment about point A. The area is 60 times 4 or 3, right? 60 times 3 divided by 2. So negative 60 over EI times 3 divided by 2. And there's no area here, by the way. So this area multiplied by the distance. And where's the distance? It's from 1/3 from the edge here to point A. So in that case, that's what you have. So this is 2/3 of 3, which is 2, plus another 1 meter distance that you have. Okay. And again, remember, no area here. And from there, you get your TA with respect to C. And since we have now both these values, we can just add them together. And again, and I emphasize this a lot, I know, but negative, don't worry, again, we just add the absolute values. Negative, positive, the only meaning of that negative value there is that this point on the curve is below the tangent drawn, which makes sense, right? Which confirms that we have drawn our elastic curve correctly. That's all it means. But you're just going to add them up like this, 580 plus 270, just absolute values basically. And once you do that, you get your deflection, and the direction is downwards, as you can see. Original state, deflected state, so it's going down. And that's it for this problem. If you have any questions about this video, please comment them down below, and subscribe for more content about structural engineering problem solving. Thank you for watching, and see you in the next video.